Good day everyone. This project focuses on the design and simulation of a folded cascade CMOS operational amplifier as a part of the Analogue integrated circuit design course. The folded cascade topology is selected because it provides high voltage gain while maintaining good stability and reliable operation under low supply voltage condition, which is important in modern CMOS technology. In this project, the amplifier is designed using a PMOS refresher input stage and NMOS folded cascade branches to enhance output resistance and gain. The circuit is implemented and simulated using Siemens EDA tools. Its performance is evaluated through DC analysis to verify correct biasing, transient analysis to study time domain behavior, and AC analysis to assess gain and stability. The simulation results are then compared with the expected performance target proposed in Part 1 to validate the overall design.
Hello everyone, today I will explain our CMOS amplifier design. It starts with a PMOS differential input pair that takes Vin positive and Vin negative. This is combined with NMOS folded cascade branches, which raise the output resistance and gives us higher voltage gain. To keep the circuit stable, we use bias voltage sources at 2.5 volts, ensuring all the transistors stay in the saturation region for linear operation, with the VDD as 5 volts. Current mirrors help replicate and control bias currents across the design. The most transistors are sized with W as 17 micron and L as 10 micron, which provides good matching and supports high gain operations. Finally, the amplifier delivers a single-ended output at V out positive, making it ready for further signal processing. In short, this design achieves high gain stability and precision through a PMOS input stage, NMOS folded cascade branches, and careful biasing. We also made few changes to the circuit, as in using only one output source and using VDC instead of common mode feedback voltage to get more accurate waveform than a complicated one. That's all for the circuit.
So now let's discuss about the DC characteristics. The DC characteristics plot illustrate the operating point of the folded cascade operational amplifier under steady-state conditions. From the graph, the output voltage settles a constant value within the supply range and does not drift toward either rail. This behavior occurs because the biasing network establishes stable drain currents in the folded cascade branches, ensuring that all MOS transistors operate in the saturation region, where the drain current is largely independent of the drain to source voltage. As a result, variations in node voltages do not significantly affect the output, leaving a well-defined and stable DC operating point. This confirms that the bias voltages and the current sources are correctly designed and that the amplifier is properly biased for the subsequent transient and AC operation. So for the key observations from the DC graph. Firstly, the output voltage remains constant over time, indicating a stable operating point. Secondly, no rail-to-rail saturation is observed, confirming sufficient voltage headroom. Thirdly, constant DC level implies that all transistors remain in saturation. Fourthly, stable bias currents prevent drift in internal node voltages. Lastly, correct DC biasing enables linear amplification in later analysis.
Next, this slide shows the transient characteristic of the folded cascade operational amplifier, where the output voltage V out positive is observed in the time domain. From the waveform, the output voltage fluctuates predictably around a constant DC operating level of approximately 50.57 microvolt, indicating that the amplifier remains properly biased throughout the simulation. The waveform maintains a consistent shape and amplitude over multiple cycles, which show repeatable and stable time domain behavior. No clipping or flattening is observed at the peak or valley, confirming that the output remains within the allowable voltage headroom and that none of the transistors are driven into saturation or cut off. In addition, the transition between peaks are smooth without abrupt change or delay. This indicates that the circuit responds reliably to time-varying conditions. Finally, the absence of ringing, overshoot, or irregular oscillation confirms that the amplifier exhibits stable transient operation and does not show underdamped or unstable behavior in the time domain.
So for the gain and phase margin, as we can see here, the pole magnitude plot shows a high and constant low frequency gain, nearly equal to 65 dB, due to the large output resistance of the folded cascade stage. As frequency increases, parasitic capacitance introduce dominant poles that cause a gradual gain role of indicating controlled pole placement and extended bandwidth. The phase plot decreases smoothly and at the gain crossover frequency, the phase remains above 180 degrees, giving a positive phase margin. So this confirms that the amplifier is stable and unlikely to oscillate in closed-loop operation.
I am Ahmad Fakrul Najmi, and this is the discussion of our project. When comparing the simulation graphs with the expected result proposed in Part 1, strong agreement is observed. The DC graph confirms the predicted stable bias point, the transient waveform matches the expected undistorted time domain response, and the AC plots demonstrate a gain level and roll-off behavior consistent with the initial design targets. Minor variation in slope and corner frequency can be attributed to non-ideal effects such as parasitic capacitance, infinite output resistance, which were not fully accounted for in the preliminary hand calculation. To conclude, a folded cascade operational amplifier was successfully designed and simulated using CMOS technology. The DC analysis confirms proper biasing and stable operations where most transistors in the saturation region. Transient analysis shows that the output follows the input signal without distortion, while AC analysis demonstrates sufficient gain and stable frequency response. Overall, the simulation results are consistent with the expected output proposed in Part 1. Based on the DC, transient, and AC simulation graph, the folded cascade operational amplifier exhibits correct biasing, stable time domain behavior, and sufficient frequency domain stability. The flat low frequency gain region, control gain roll-off, and positive phase margin collectively confirm that the amplifier operates as indeed intended. This graph-based result validate the design choice made in Part 1.